Have you ever watched an excavator digging and wondered how the bucket moves so smoothly and precisely? Even though the operator is only moving a few joysticks, the bucket can reach deep into the ground, curl perfectly, and dump material exactly where needed. This smooth motion is not accidental. It is the result of excavator kinematics, the science of how different parts of the excavator move together. Excavator kinematics explains how the boom, arm, and bucket move together to place the bucket accurately at any point in space. It does not talk about forces, pressure, or power. That part is called dynamics. Kinematics focuses only on geometry, such as link lengths, joint angles, and motion relationships. This geometric understanding is the foundation of excavator design, motion simulation, and modern automation. Without correct kinematics, even a powerful excavator cannot move smoothly or predictably. An excavator front attachment can be understood as a mechanical chain made of rigid parts connected by rotating joints. Starting from the upper structure, the motion flows through the boom, then the arm, and finally the bucket. Each connection allows rotation, so engineers call this a serial kinematic chain. Most digging motion happens in one vertical plane, which makes this simplified model accurate enough to study how the bucket moves. Each part of the chain has a specific role. The boom raises and lowers the entire working area. The arm controls reach and digging depth. The bucket performs digging, curling, and dumping. Even though hydraulic cylinders move in straight lines, the joints rotate. Kinematics explains how straight-line hydraulic motion is converted into smooth angular motion at each joint. Hydraulic cylinders are not placed directly at the joint centers. Instead, they are mounted at an offset, forming a triangular arrangement with the links. When a cylinder extends or retracts, the shape of this triangle changes. This change in geometry forces the joint to rotate. One of the most important concepts in excavator motion is forward kinematics. Forward kinematics answers a simple question. If we know the joint angles or cylinder positions, where exactly is the bucket tip? Engineers simplify the excavator into a two-dimensional model and calculate the bucket position using geometry and trigonometry. This allows them to predict reach, digging depth, and dumping height. If the boom length is denoted as L1, the arm length is L2, and the effective bucket length is L3, and the corresponding joint angles are θ1, boom angle relative to the base, θ2, arm angle relative to the boom, and θ3, bucket angle relative to the arm. The bucket tip position in Cartesian coordinates can be obtained by vector summation of each link contribution. The horizontal and vertical coordinates are expressed in this equation. Each term in these equations represents the projection of an individual link along the horizontal and vertical axes. The cumulative angles, θ1 plus θ2, and θ1 plus θ2 plus θ3, arise because each downstream link rotates with respect to all upstream joints. This cumulative effect is characteristic of serial kinematic chains and explains why small changes in upstream joint angles can significantly influence the final bucket position. In engineering practice, these equations are embedded within CAD motion studies and multibody simulation tools to evaluate the excavator's working envelope. By sweeping the joint angles across their allowable ranges, engineers generate reach curves, depth profiles, and dump height envelopes. These plots directly inform design decisions such as boom length selection, arm proportioning, and bucket size optimization.